Welcome everyone to More Agile Than Agile, a layered approach to MBSE, presented by Zane Scott. My name is Donna Long and I will be your host during today's webinar. As Vice President of Professional Services at Vitech, Zane manages the company's consulting and training organization. For the past 25 years, Zane has built a skill set that enables him to provide insight and guidance to individuals and companies as they improve organizational processes and methodologies. Zane has also taught systems engineering methodology in a variety of settings, is a frequent blogger, and is co-author of Vitech's book, A Primer for Model-Based Systems Engineering. Before joining Vitech, Zane worked as a senior consultant and process analyst, assisting government and industry clients in implementing and managing organizational change. Before Zane gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Zane will answer as many of these questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be available within 1 business day. The recording will be published to Vitech's webinar archive, located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you would like to see covered in future webinars. Now I'm going to turn the presentation over to Zane. Welcome, and thank you for joining us.
Thanks, Donna, and welcome to everyone this morning. We're pleased that you could take some time to be with us, and we want you to have hopefully an enjoyable and perhaps enlightening experience with us this morning. Our topic is going to be something that is rather a hot topic in a number of different fields now, and that is what is known as Agile or Agile development. It's a methodology, a system that began in the software industry and has now advanced to become talked about in a number of different disciplines: Agile management, Agile systems engineering, Agile engineering. So what we'd like to do today would be to talk about Agile and its relationship to model-based systems engineering. Our idea in presenting this is that we have noticed as we practiced model-based systems engineering that there are a number of striking similarities between MBSE and the principles and concepts of Agile. And so we want to suggest to you today that model-based systems engineering answers the questions that are raised by Agile, the concerns that are raised by Agile, and is arguably even more Agile than Agile. So let's get started by talking about a little bit about the genesis and the beginning principles of Agile. Agile began with an expression of concern over a number of areas, and the Agile Manifesto, which was the seminal document that kicked off the entry into the Agile world in the world of software development, expressed a number of values. First, it values individuals and interactions over processes and tools. Agile asks that we not get lost in processes and tools and forget to value the individuals and the interactions between the individuals as they engage in the development process. It values working software over comprehensive documentation. Sometimes in an effort to get comprehensive documentation, we can get lost in the document weeds, and Agile encouraged us to be more focused on working software and less focused on documenting the process and the software as we go. Agile values customer collaboration over contract negotiation. So we don't engage with the customer in a contract negotiation that seals the bargain and draws a boundary around our interaction with the customer. The interaction and collaboration with the customer does not and should not end at the point of a signed contract. And finally, Agile responds to change and values that over following a specific plan. So as things occur, as we discover, and we'll talk about this a little later on, but especially with regard to complex systems, as we discover aspects of the problem and of the potential solutions that require us to change our stance, we're flexible about that. We welcome that change rather than become resistant to it. So we recognize that it's really not possible to set a plan that's going to completely survive contact with the problem. Those values that were expressed in the manifesto are embodied in 12 different principles. And these are the principles that drive Agile. These are the principles that we're going to talk about today. The first of those is the highest priority is satisfying the customer. And it talks about doing that through the early and continuous delivery of valuable software. As we translate Agile into the development of systems, you can read system solutions wherever you see software in the original Agile Manifesto and principles. We welcome changing requirements, even when those changes come late in development. The changes need to come when they need to come, as opposed to saying arbitrarily, this is the cutoff point, no more changes beyond this line. So that balance is struck by being welcoming of the changes in requirements as they occur. The third principle is to deliver working software, working system solutions, as I pointed out, frequently. This means that we continuously try to stay with working solutions, try to address that as opposed to building a collection of parts that are not useful in any sense until we get to the very final stage of putting it all together. Business people and developers must work together daily throughout the project. In that sense, you need collaboration that occurs on a regular and frequent basis so that you're constantly checking yourself to make sure that you're on course. You build projects around motivated individuals, give them the environment and support they need, and trust them to get the job done. And that's a piece of what we need to do with respect to designing system solutions, as well as what you would do in designing software. The most efficient and effective method of conveying information to and within a development team is face-to-face conversation. That's one that's not methodology specific. That's one that is not a product of your method as much as it is a product of the way you organize and conduct yourself. Working software is the primary measure of progress. In our sense, in the sense of talking about systems engineering, working solutions are the primary measure of progress. Agile processes promote sustainable development. The sponsors, developers, and users should be able to maintain a constant pace indefinitely. In other words, we do our work in a way that enables us to constantly move forward, that is not firefighting or running to a particular deadline to the point of exhaustion. It doesn't depend upon heroism. The process sustains itself. We pay continuous attention to technical elegance and good design. which enhances the agility of the process and the quality of our ultimate product. Simplicity, the art of maximizing the amount of work not done, is essential. We need to look at what we do and constantly ask the question and promote in the process the ability to not do things that are not necessary, to allow the methodology to take care of and our tools to take care of work that can be done by them rather than done as an extraneous part of what's going on. The best architectures, requirements, and design emerge from self-organizing teams. This works in the Agile environment. It also works in the model-based systems engineering environment, and each team can tailor its own organizational schema to how it can best be organized, irrespective of whether we're talking Agile or model-based systems engineering. At regular intervals, the team reflects on how to become more effective, then tunes and adjusts its behavior accordingly. That too can happen. It's not methodology dependent. So when we look at these principles, when we begin to look at Agile and model-based systems engineering, we see that of the 12 principles, model-based systems engineering promotes 9 of those in and of itself and allows for the other 3 to happen. So 9 are directly satisfied by MBSE, and 3 are not methodology specific either to Agile or to MBSE. So we begin to see taking shape a similarity and an ability to leverage the Agile values in either one of these approaches. Boiling down the principles, as we'll discuss them, we get shorter statements. Our highest priority is to satisfy the customer. We welcome changing requirements. We deliver solutions frequently. The stakeholders and solution designers work together daily. We build projects around motivated individuals and give them the environment and support they need and trust them to get the job done. Working solutions are our primary measure of progress. Agile processes promote sustainable development. The sponsors, developers, and users should be able to maintain a constant pace indefinitely. Continuous attention to technical excellence and good design enhances agility and simplicity. The art of maximizing the amount of work not done is essential. These are the Agile principles restated in a way that they can be applied to systems development as well as to software development. So where do we start? Let's talk about the model-based systems engineering process and begin at the starting line. Begin with the MBSE principles as we see them at the very beginning of a project. The first principle is that we begin high. We take a high-level view of the problem, the context system that the problem lives in, and of the potential solutions that we might apply. We do that for 3 reasons. Beginning high promotes innovation. It allows us to be innovative in the way that we look at the problem, and it allows us to be innovative in the way that we look at the potential solutions. Secondly, it gives us the vision to be able to see the problem, to be able to see the potential solutions, to be able to see where we're going, which direction we need to go at various decision points. And the third consideration here is that it keeps the alternatives in front of us, that it opens us up to the whole spectrum of alternatives for solving the problem. the alternative or potential solutions are are available in the broadest possible spectrum. So how does it promote innovation? Well, the innovation process basically can be divided or thought about in three different segments. And I've used a gradient here rather than three columns because these sections are iterative, so you don't move down this curve in a particular order, but you go back and forth to some extent, moving back and forth between the stages. You begin with the inspiration stage where you have a lot of prototypes, and you can think of prototypes here as ideas about how we're going to solve the problem, ideas about what solution is going to be appropriate. So there'll be lots of those in the very beginning, lots of different ways of looking at things. As you progress, as you begin to narrow your solution and follow the MBSE process, you find that two things happen. We spend a lot more time developing our prototypes. They become more detailed, more granular. They become more well-formed as we get into the ideation stage. And the number of prototypes that we consider begins to narrow down as we try to focus on an ultimate solution. And finally, in the innovation cycle, we get to the validation stage where we have a pretty well-formed idea of how we're going to solve the problem, and we begin to validate that back against what is appropriate as a solution. So beginning high enables us to enter this innovation process at the most advantageous level and to work that process down through to validation, having considered and made intentional choices about the greatest number of alternatives. Part of this comes from the increased visibility. If you notice, this is a picture of an entryway to an apartment complex. So if you want to go somewhere, you go out that entryway and you're immediately faced with the choice of going right or going left. You need to decide which way to go. At a low level, that's a very difficult decision because you don't have enough vision into, if I turn right, where does this road go? And how does that sit in relation to where I want to go? Or if I turn left, where does that route go? But if you raise the level of your view, if you begin high in making your choice, and we do this not by climbing way up in a tree or on a utility pole to look down, we look at a map, we adopt a higher view, or we understand from our experience the layout of the street system. So now with the higher view, with the increased knowledge, we have a better formed idea about how we might get to where we're going. We can see where we're going and we can see what the potential routes are to get there. So by beginning high, we get a broader vision, which helps us to understand the lay of the land as we enter the problem-solving process. Beginning high also enables us to keep the greatest number of alternatives open. If we begin where the Q is in that box, then we have 3 alternatives available to us, and we have alternatives below those that grow out of the alternatives that are available to us coming straight out of Q. So we have a number of different directions that we can go. But if we decide that we're going to begin where the star is, then we are limiting ourselves. All of a sudden we find that our choice of alternatives is somewhat limited because we've begun at a lower level to choose what we what we tend to look at. And the alternatives that are grayed out are cut off to us. They're visible from Q, but they're not visible from where the star is. So if we begin at that low level, then we've lost a number of alternatives that would be possibilities had we begun higher. So the first principle is to begin high. Now we can see how that applies in greenfield development. How does that apply to a novel solution, a first-time solution to a particular problem? But increasingly, as we get into engineering solutions to problems, we deal not with the greenfield, but with the brownfield of existing systems. And so we get into what's called middle out engineering, where we take a system and begin with it and develop an understanding of that system and then make improvements to it. Well, the interesting thing is when you look at the process for greenfield development, you see that we begin up at the top. So we begin up there where it says 0, with time going from left to right across this timeline. The first activity is to define the need and the system concept. And then we work toward the selection of a design. And we engage in these activities as we move forward to converge on a solution. If we, on the other hand, begin with a problem that is reverse engineering or middle out engineering, what we find is that we begin with our activities in a reverse order to a certain point. So we begin to study the system, look at the system boundaries, capture the interfaces, capture the component hierarchy. We begin to look at what's going on in the system that we have until we get to a point where we feel like we can take the problem considerations and update the system boundary and begin to modify what we see in the existing system, and through those modifications converge on a design. This is just another version of approaching the problem from a high level. We work our alternatives to go up the side of understanding the existing system so that we can then go down the side of converging on a design. So in either case, we are getting to a high-level viewpoint in order to be able to see the problem and the alternatives and the potential solutions. Well, let's talk a little bit about the principles of model-based systems engineering. Let's begin with the fundamentals. The first fundamental that we begin with is that model-based systems engineering is based in a single model. That doesn't mean we don't use other models. That doesn't mean that there are not other models that are possible that can provide us with information. But the model that is the basis, the model that makes model-based systems engineering model-based, needs to incorporate all of these elements into a single integrated model. And there's a very, very good reason for that. And that is, in any system, the power of the behavior of the system comes from the interactions among the entities and elements of the system. So it's how the behavior interacts and relates to the requirements and the architecture, and how the requirements are fulfilled in the architecture, and how we test, how we verify and validate. All of the interactions of those entities in the system need to be included in the model so that we can see the interactions and see the true power of the system. If we break those apart, and there are a number of ways that we can break those apart. We can put those into compartments. We can have a separate requirements model, or have an architecture model, or put them in different tools. We put them in different boxes, or we make drawings that address one or the other of them. When we do that, we break the relationships and the visibility of the relationships, which breaks our understanding of the system. So we're looking at an overarching model that includes all of those domains. We need to work in all 4 domains too, constantly, as we move through the process. That way, we don't forget the development of a particular domain, and we eliminate the rework that can come about when we discover down the line, whoops, probably should have thought about that. Now I need to go back and do rework and make changes, and you wind up with a lot of back and forth. In the traditional or waterfall model, everybody disclaims the waterfall model as an approach, but lots of people use it anyway. But in the waterfall model, the idea was that you would come down the stream and you would go over the requirements waterfall. You would drive all your requirements to ground. Once you had your requirements to ground, then you could derive the necessary behavior. You move that all the way to ground, and then you design an implementation system that addresses that behavior. And finally, you go back and verify and validate your final solution. But in a layered MBSE approach, you begin at a high level. You begin with low granularity and a high level view of the problem, the context, and the potential solutions. And you begin to think about, okay, at a high level, what are my requirements? And at a high level, what does the system need to do? How does it need to behave? And at a high level, how could that be implemented? And is this high level definition of requirements and behavior and implementation, will that really solve the right problem? Are we after the right problem? In other words, we validate it. And are we on the right track? Does it actually do that? So we verify it. Then we move to the next level of granularity. And we begin at that point to work across the model. What it's difficult to show here is that we iterate back and forth. So we don't do all of requirements and all of behavior and then all of implementation. But we move back and forth, working in all 4 domains at each level of granularity. We know that we're done when we get to the level of granularity that allows us to specify a solution that can then be built and implemented and live out the rest of the life cycle of the system successfully. But we drive at that solution in a layered approach. As we move, it's all about relationships. Requirements are the basis of behavior. Behavior is allocated to the components. The components perform the behavior, and the behavior is based on the requirements. That's the fundamental schema behind model-based systems engineering. And actually, that schema is derived from reality, not imposed on it. It's a positive schema, not a normative schema. So you've heard it said that if you want to know what somebody's real priorities are, look at their checkbook. And what that means is their checkbook represents how they behave, what they do. So if you want to know what requirements really drive them, look at what they really do, because that's driven by what they think they ought to do, what they, quote, want to do. But their actual behavior reflects their actual requirements, because requirements are the basis of behavior and behavior is based on requirements. Then you can look at their implementation system, what's often referred to as the physical architecture. But their implementation system makes their behavior possible because their behavior is allocated to the implementation system, to the components, and the implementation system performs the behavior. And throughout this schema, we want to verify and validate. When we validate, we determine whether or not we're meeting the right requirements. So I might say that I want to save money for college, but my behavior won't validate with that because I'm actually spending the money that I'm earning at my summer job to buy an automobile. So my behavior reflects different requirements than I've stated, so it won't validate against my requirements. Verification is the other side of that coin. We verify that the behaviors actually will satisfy. The implementation structure will satisfy, it will perform the behavior, and the behavior will satisfy the requirements. So validation has to do with effectiveness, or effectiveness, and verification has to do with efficiency. We do this by increasing the granularity of the solutions that we consider. So we begin at a high level without defining much granularity, and we increase the granularity as we go, and we zero in on the solutions that we're going to apply to the problem following that innovation cycle that we talked about. So we make orderly decisions, and we're complete at any given level of granularity. So we have complete solutions. Now let's talk about some issues around using models before we move. The first issue is, what is a model? And perhaps even more important, what is not a model? So what you see, a plastic airplane, a mathematical model, a fashion model, all of these are models in some sense of the word. But what sense do we consider a model? Well, for our purposes, a model is always a limited representation. So it's not the actual airplane, but it's a representation of the airplane in some form. And that limited representation has to include all the information relevant to the purpose of the model. So if the purpose of your model is to show the appearance of an A10, then the plastic model that you see down in the right-hand corner does that. I can remember as a kid building models of the P-51, which we were interested in because my mom's brother was a P-51 mechanic who became a research scientist for NASA. And one of the things that we strove for was to paint the P-51 models that we made with his unit, the paint scheme and the labels and the appearance. We wanted it to look like the P-51s that our Uncle David had worked on. And so to the extent that the model represented that, then it was useful. It was useful because it fulfilled its purpose, and it fulfilled its purpose by containing everything necessary to do that. So for MBSE, models are limited representations of a system or a process, and they can be migrated into a cohesive, unambiguous representation of that system. In other words, it can be used to construct the solution system itself. So in model-based systems engineering, the model really is the system specification. And ultimately, the system specification becomes the model. The visualizations of that system specification are derived from the model. And the model rests on the logical architecture, the function. So what we're ultimately trying to model is the system behavior that satisfies the requirements. Now we get confused sometimes because views are a limited representation. So in some sense, a view is a model, but they're not MBSE models. Views of the MBSE system solution flow out of the model. They come from the model. They are not the MBSE model. So what is a view anyway? A view is a structured answer to a request to the database for a particular subset of information from the model that's contained in the database. So where we have a model and we've surfaced that model and made it available for work and visibility, then what we're doing is posing a query to the model. Give me this subset of information about the model. And by the way, I want my answer delivered according to a set of rules. And the rules are the rules for creating the display of that information in a particular format. In this case, as a SysML activity diagram. So I want this information about the activities of the system, and I want it displayed according to the activity diagram rules. The question becomes, where is the model? Do we have the model contained in such a way that the views can be generated from the model, or is the model simply in the head of the designer? So if it's contained simply in the head of the designer, then the query has to be to the head of the designer, and the designer has to draw the answer according to her understanding of the rules for making that view. So it becomes a more difficult process, and it becomes a less efficient and less effective way of producing a view of the model, because the model is not manifest. It's contained in the head of the designer. So we want to generate a model, but we want to be able to generate our views out of the model rather than out of the head of the designer. So let's introduce MBSE to Agile and see how that introduction goes. We'll take the principles and compare the principles as we move through. The customer is the key. We validate at every layer and we maintain traceability. Those MBSE principles go a long way towards satisfying the Agile priority on the satisfied customer. In both MBSE and in Agile, our priority is satisfying the customer, coming up with a solution that solves the customer's problem. In order to do that, we maintain full traceability. What those of you who are familiar with CMMI would understand as bi-directional traceability. In other words, requirements are the basis of functions. Functions are allocated to an architecture. The architecture performs the functions, which are in turn based on the requirements. By doing that, we maintain a full ability to satisfy the customer and to be sure that what we are doing, what we are adding and subtracting from the design, is done in the name of a satisfied customer. So both Agile and MBSE work toward that principle. The second principle that we look at is changing requirements don't disrupt our orderly layer transitions, because the model is holding everything in relationship. This is particularly true where the model is embedded in an integrated way in a tool, rather than just in the head of the designer. If the model is going to be in the head, ultimately in the head of the designer, that imposes a very heavy burden, especially as you get into the realm of complexity, because it becomes extremely difficult and at some point impossible to hold all that in your head. But because you have that, and because you're moving in an orderly way through the layer to layer transitions, we can welcome changing requirements rather than oppose them. Because when we make changes at whatever layer, we can simply move among the 4 domains and reflect those changes and verify and validate those changes within the other 3 domains. The third principle is that the end result of each layer is a complete model. At that level of granularity, you have a complete model in MBSE. The Agile Principles ask us to deliver working solutions. It calls it working software originally, but it calls on us to deliver working solutions frequently. In MBSE, with a layered approach, you deliver them layer by layer, regularly and frequently. So you move through with increasing granularity, but at any given layer, you've worked in all 4 domains, you've done your verification and validation of your requirements, behavior, and architecture, you've documented at that layer. And by the way, documentation is simply another kind of view of the model. So any given documentation is obtained by querying the model for the information necessary for the documentation and displaying it in the format. To the extent that you can leave that to your database and leave that to your tools, you're taking the burden away from the designer and placing it in the lap of the tool. So we have solutions that become available on a regular and frequent basis. The fourth principle, by surfacing the model, everybody can see it and we can choose the appropriate view. That enables the stakeholders and designers to work together. So when we have the model surfaced in a tool and available, we can generate the views that are appropriate, and stakeholders and designers can understand what's in the model, what's not in the model, why it's there, why it's not there, and can make suggestions about the direction that we're going, affirming it, changing it, heading in another direction. But we can work together regularly. How do you determine what views? The view that's appropriate is based on who is the audience. First, we ask who are they and what will speak to them. So if you take a group of business people used to flow charts and show them an N squared diagram, they're going to come away probably confused at best. So the view that appeals to them is going to be an enhanced functional flow block diagram, or an activity diagram, or maybe even a sequence diagram. So first we ask who are they and what will speak to them. The second thing we ask is, what do they need or want to know? Why are they wanting to look into the model? Why do they need to look into the model? And only thirdly do we ask, what do we need for them to know? What is it that we're trying to convey? What's our message? If we don't first address what they need to know or what they want to know, then we won't be able to get to the level of conveying what we need for them to know. So that's how we choose a view. Answering those 3 questions tells us what view is going to be most important. The 5th principle has to do with team collaboration. The model provides discipline, and the team can focus on problem solving. So teams can look at the model, and by looking at the model, they can collaborate in real time. This is what it takes to give them the needed environment and support for their decision-making and problem-solving processes. The sixth principle is that we need to be able to measure progress and deliver working solutions. We do that by verifying and validating at every layer. So as we increase the granularity and move layer to layer, we are sure that as we come away from the previous layer, that everything is verified and validated, and we're beginning at a valid, verified point. And we move through all the domains and verify and validate again as we move into a new layer. The seventh principle concerns orderly work. The model manages complexity. As you build the model actually disciplines your process. The problem doesn't become overwhelming because you're being asked to manage the complexity all in your head, testing your memory and your calculating strength, if you will, between your ears. You put the management of the complexity and the ordering of the work into the tool, into the model. And that enables us to maintain a constant supportable pace. We don't get to a point where everything implodes because it's become so complex we can't deal with it. It means that when we make changes and as we develop our solution, that we maintain consistency and completeness in the model. And we don't have to sit down and say, okay, I've got this kind of diagram here, and it shows me that I need to add a function, say. Well, if I add a function, then I've got to go back to all these other drawings that I've made, and I've got to figure out, how does this addition figure into each one of those drawings? And I have to make those changes by hand. The eighth principle talks about integrity and completeness and intentional design decisions. We don't get forced or boxed into design decisions, and we ensure our integrity and completeness as we go, which leads to technical excellence and good design. We use one integrated model, and the model and the tool manage the integrity and completeness. Ninth principle, just because views and documentations are generated by querying the model, there's no need for that repetitious clerical work. So you don't have to go back and manually track through every representation and make sure that it's up to date. You can reuse pieces of the model, so you're not reinventing the wheel at every turn. So using the model allows you to maximize the amount of work not done. We don't have to do that clerical work. We're not called upon to produce reams and reams and reams of useless documents that are simply changed and made irrelevant. And we don't have to go through and manually make changes. So let's look at the values. We've looked at the principles of Agile. Let's look at the values. Agile values individuals and interactions. The model focuses the work on the design tasks. It frees engineers to be engineers, and it gives them an enhanced basis for communication. So individuals and interactions become the focus rather than documentation. We want working solutions. We value working solutions at every juncture. And the focus with model-based systems engineering is on problem solving, not on drawing views or creating documents, because you can do that out of the model with your tool as opposed to doing it by hand. Excuse me. We value customer collaboration. With a model and a tool that are fully capable, we can choose from a wide menu of views. We can choose the views that will speak to the particular audience and enable their collaboration. So we're able to collaborate with the customer. We can respond to change because we maintain full bi-directional traceability at every juncture. So the model holds everything in relationship. If we make a change, the impact is immediately traceable into the model and back and forth through the schema. So we have that impact tracked, and we have that done automatically, if you will, in the model, and we're not forced to stop and try to consider everywhere such a change would have an impact and necessitate other changes. So how do we sum this up? If we use model-based systems engineering, how does it benefit the enterprise? And I think what you'll see is that it benefits the enterprise in much the same ways that Agile is able to benefit an enterprise. Model-based systems engineering enhances communication. It promotes a shared understanding, and it provides rich representations which can speak to whatever audience needs to interact with the model and collaborate in the process. It reduces your development risks. It allows you to identify requirements issues early on. Not only can we deal with changing requirements that come at us externally, but we can identify and deal with requirements that have to change because of ways in which the solution develops itself internally. We have a faster requirements cycle, which means that we can improve our cost estimates and maintain our accuracy and know where we are. We can have both early and ongoing requirements validation and the verification of the design. And we have a disciplined basis for decision making because we can see the impacts and trace the impacts into the model. The quality of the solutions is improved. We have enhanced system design integrity because it's done automatically in the database, in the model. We have improved specification of allocated requirements to both the hardware and the software, and that leads us to fewer errors during integration and test. We have more rigorous traceability all the way from the needs through the solution and back again. We can increase our productivity because the improved impact analysis of requirements changes happens more quickly and more easily than in a strictly manual system. We're able to make a rapid analysis of design changes. We can reuse portions of the design or reuse other designs as we support our design technology evolution. And we can automatically generate work products. So we generate views, we generate documents. All of that comes out of the model rather than being generated by a review and manual documentation. We have increased visibility into the design. We're able to incorporate all of the domains. We can integrate the models. We have an extension of representations and audiences. All of this promotes visibility. And it provides a structure to capture and communicate all aspects of the system. I think you can see, as we have traced our way through the principles and the values of Agile and laid them down beside the principles of model-based systems engineering, that using MBSE, particularly in a layered approach, and most importantly in an integrated model, using an integrated tool, you're able to promote the Agile values and principles as well. So that's why we like to say that model-based systems engineering is perhaps even more agile than Agile. I thank you for your time, and now I'm ready to accept questions.
Thank you, Zane. We do have a few questions thanks to our participants. I encourage you to join the discussion now and submit your questions using your webinar control panel. If you do need to leave, please take a moment before you go to respond to the quick survey that will pop up on your screen. We have a question from Mike. Late requirements might work for software or things that are easily changed. However, do you believe we can welcome late changes for large, complicated systems without incurring great cost?
Here, I think, Mike, we need to make a distinction between design and manufacture. So if you're building a ship, you can't go out and build the prow and the stern and start working together and then say, oh goodness, it can't be this wide. We need to change the width. At the manufacture stage, late requirements are going to cause a huge cost. At the design stage, when the ship is a model contained in a database that you're working on, you can make those changes. You're exactly right about software. As you write a program, you can change ones and zeros a lot easier and in a less costly fashion than bend metal and string cable. But in making the design that the manufacturer is based on, you can accept, especially into an integrated model, you can accept late changes. And once you get the design and build it, you're able to work that in much the same way that you would in the software world.
Okay. Our next question comes from Destiny. Would you say this approach needs the investment of the whole organization, requirements, software, engineering, test? How do you suggest to gain buy-in from all sectors which are comfortable with traditional approaches?
Any kind of organizational change is difficult, and you're exactly right. You have to get buy-in from all of the sectors, all of the folks who are controlling the domains. So it's difficult to change the paradigm from I'm a requirements engineer. That means I write a stack of 1,600 requirements and then I deliver that to the folks who further the design. It's a matter of changing the paradigm through which they view the process. And that can be difficult, but it also can be done. And one of the ways in which it's done is by showing the benefits. For instance, the last question asks about late requirements. What kinds of problems does that cause when the folks who are doing the design discover constraints that hadn't been considered, or the customer wants to change requirements, and back you go to the requirements people, say, I need you to make this change in your requirements, and they go through and say, well, my goodness, that's going to cause this to change. Once you see that an integrated model makes all that a lot easier, and it makes it easier to preserve the integrity, then folks can begin to shift their paradigm. But you're exactly right to call that out as a difficulty.
Okay, we have several more questions, but I want to respect everybody's time. So we're going to wrap this up and we will get back with the people who sent in questions. If you have any further questions, please send an email to Zane. You should see his email on the screen, or you can send it to me, or you can put it on the LinkedIn page. Just visit linkedin.com and search for Vitech Corporation. Thank you so much for attending today's webinar. Our next webinar will be an overview of Genesis 6.0 presented by Ron Kratzky on Thursday, May 31st at 11 a.m. The registration link will be available on our website. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Once again, thank you for joining us and have a wonderful day.